Hello, I want to speak about the meshulam game for hypergraphs. This is joint work with Hegu. So we speak about a matroid on a set V, and we want to color it with k colors. It means that we partition the set of vertices to such each of which is independent, and it's the same as weakly coloring in the hypergraph of circuits, meaning that no hyper edge is monochromatic. So this is an example, and by coloring it, we color it when no edge is monochromatic. So here, the chromatic number is 2. And we can also ask for intersection of matroids. We want that every set will be independent in all of the matroids. And this means that we color the union of the hypergraphs of circuits. So we ask what's the relation between the chromatic number of the intersection and the chromatic number of each one of them separately. And okay, let's be modest. Let's only ask it for 2 matroids. And here are some answers. So for example, in the 2 partition matroids, so actually we deal with a bipartite graph. So by Koenig's theorem, the chromatic number of the intersection is the maximum of the chromatic numbers of the 2 matroids. And it is still true for a larger class of matroids, the strongly based orderable matroids. And it's also true for general matroids, but in the fractional version. So now, what happens in the non-fractional version for general matroids? So it won't be true in this case, because here is a matroid of size where the chromatic number is 2. Here's another matroid with chromatic number 2. And if we take the intersection of these 2 matroids, so we take the union of the circuit hypergraphs, then you can check the chromatic number is actually 3. So what can we still say? Here's something we can say. This is from a paper from 2006 of Aroni and me, that the chromatic number is at most twice the maximum. So, okay, so twice of the best we could hope for. And the question is, maybe can improve it. But what if one of the chromatic number, say chi of M1, is strictly more than chi of M2? Can we say something better? And the answer is yes. In some very specific case, if chi of M1 is less or equal to P and chi of M2 is less or equal to Q, and P divides Q, then we have that the chi of the intersection is less or equal to the sum of P and Q. And for many years, I felt that this P divided Q is redundant. It shouldn't be there. And 19 years later, we could actually prove this, that you can prove the same without assuming P dividing Q. So here's what actually we have, that chi of the intersection is equal to the sum of the chi's. Let's give an example so we can see how it improves things. So say we have one matroid of chi of one matroid is 3 and chi of the other matroid is 10. What can you say about chi of the intersection? So if we just take the result of 206, then we can say that chi of M1 is less or equal to 5, and 5 divides 10, so chi of the intersection is less or equal to 15. Actually, well, it's not really written in the paper, but if you think of it, you can do this with the same methods. You can say that chi of M1 is less or equal to 10 thirds, and 10 thirds divides 10. So chi of the intersection is equal to 10 thirds plus 10, but you should round up. So it's 14. And the new result says that you can actually say 10 plus 3 as they are. You don't need anything to divide anything and get 30. So let me say a few words about how we prove this. So the main idea in the proof of this, in both, also the proof from 2006, is to use topological methods. The intersection of matroids is an abstract simplicial complex. Every subset of an independent set is also an independent set. So we can study it by studying its topological property. So here is the topological property that we will study, and this is the eta parameter. Eta parameter is the topological connectivity plus 2. So what do I mean with this? Well, okay, so it's the maximal k for which for every j up to k, if I have a j minus 2, if I have a function from j minus 2 to the complex, then I can fill the inside of it with the complex. Or another thing is to say that eta is the minimal dimension of a hole in the topological structure. And a theorem of Aaronian Huxley, but this is reformulated in many sense, but it says that if for every set X of vertices we have that chi of the complex obtained on these vertices is at least chi of complex induced on the chi of the complex induced on the is at least the size of X over K. If this is the case, then C has a column with K colors. So for coloring a simplicial complex and abstract simplicial complex, what we need to do is find lower bounds for chi. Sorry, for eta. And one way to obtain such lower bounds is the meshulam game. So the meshulam game, we have a zero-sum game on a graph whose value gives a lower bound on the independence complex of the graph. So we have a graph, and we have two players. Player one chooses an edge in each of her turns, and now player two can do one of two things. She can either just remove the edge, or she can blow up the edge. What does it mean blowing up the edge? It means we remove the two vertices of the edge and all the neighbors. So this is what is left after this blow up. And if at some point there is some isolated vertex, then the value of the game is infinity. If not, then the value of the game is the number of blow-ups. So this is a nice way to obtain lower bounds for eta. But the problem is that we can't use it here because unless a matroid is a partition matroid, we have circuits of size more than 2. And this means that the hypergraph of circuits will be more than 2. So even if we have two matroids, even if one of them is a partition matroid, if the other is not a partition matroid, is any matroid other than partition matroid, we cannot use this meshulam game to obtain lower bounds for eta. So the idea to solve it is It was found independently by Gu and me and by Demet Thailand. And it was a version of meshulam game for hypergraphs. So let me explain a bit about the differences. So one difference is that the payment that player 2 needs to pay player 1 when blowing up an edge, it's not always 1. It is the size of the edge minus 1. So if I blow off an edge with four vertices, I need to pay $3, not just 1. And the other difference is that when I blow up an edge, if some of the vertices of the edge are in some edge with more than two vertices, then I still keep the edge with the other vertices. So I had an edge with 3 vertices, now I have an edge with only 2 vertices. And other than that, the game is the same. I continue this game until either all the vertices are gone, and then I sum up the payment, I sum the size of the edges minus 1 for all the edges that I blew up. Or if at some point I obtain some isolated vertex, then the value of the game is infinity. And this still gives us a lower bound for eta. So, okay, this doesn't end the story. I need to somehow give a strategy on this game. And this is what we did. We took 2 matroids. We saw that each time we can play this game until you can do one of 2 things. You can either take one vertex and take it out of one of the matroids so it will become free, become a core loop in one of the vertices, or you can contract some circuit in one of the matroids and get to some place where you can use induction. But eventually we get what we need. We get that the eta of the complex induced on any set I want is at least the number of vertices in this set over P plus Q, and this is what we need in order to color the intersection of 2 matroids with P plus Q colors. Okay, I want to say that the conjecture that we still believe in is that if the 2 matroids have different chromatic numbers, then the chromatic number of the section is actually the maximum. And if they have the same chromatic number, then it's the maximum plus 1. It means the mutual chromatic number plus 1. But for this, I guess we need the other methods. Okay, thank you for listening, and goodbye.